Okay, morning. So fuck you. I'm gonna keep going with this. The bad thing is, I want to do like at least, well, I don't know, around 5 hours daily. But I've been doing just at most 2 or 3 hours. Sometimes even less. Alright, there's no point in regretting this shit or lamenting. So let's just get to it, okay? Yeah, it is lamenting. Fuck yeah. Okay, let's go. Let's go. No, yeah. I like this one, even though it looks so fucking. Yeah, let's put another video. Neon City, huh? I like that. Neon City, Song Island. What is this? Yeah, it's kind of interesting. What are they doing though? Oh, they're producing. I don't know. I just yeah.
Choco, 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 pum, papá. Racatuntita. Chúpame los huevos y dame la bola. Chúpame los huevos y dame la bola. Chúpame los huevos y dame la bola. Bola. Chúpame los huevos y dame la bola. Chúpame los huevos y dame la bola.
Mutually pretend the brackets aren't there. Yeah. Wait, what the fuck? And immediately guess that image browser the server because infinite. Yeah, but that's different shit, man. What the fuck are you talking about? That's different. That's total different. What are you talking about? That's different stuff. Oh yeah, I asked him, yeah, as AI to explain me this shit. Milliseconds because your stopwatch is basically the screen. Okay, you can measure how many milliseconds just. Yeah. So yeah, I mean, it's perfectly continuous and infinite. Yeah. Without blowing past 1 and 0. In a continuous model, the probability of landing at one infinitely precise is a mathematical point. That's so interesting.
Know a little bit about random variables. What we're going to see in this video is that their random variables come in two varieties. You have
Continuous random variables is the same as continuous models. The probability of a probability. Fuck, man. Lots of probability can take, depending on what you're trying to model. Wait, hold on. Oh my god. Standard normal distribution. Interesting. This is visual. Maybe it's not visual. Bro, don't talk about us like that. You're a motherfucker. You're not human, man. That's what I have to say. All right. So poisson versus beta. Beta continues. This one is crazy. Yeah, set builder notation. Yeah. So such as, such that. M is the set of. All this bullshit. All coordinate pairs, x, y. Yeah, all coordinate pairs, such that something's written as a column. Okay. Oh, I thought you were making a happy face, man. Such that x minus y, absolute x minus y, less or equal than 1/4. The absolute difference between x and y. Yeah. Where's this? What the fuck? Oh, where x is between 1 and right. Wow. Wow, this is amazing. Beautiful. I don't think
Discrete random variables.
I don't think so. Visual Painter. Discrete number variables. I should be watching this, man. This chapter 5. I mean, this lecture number 5. Okay, whatever. Let's keep going. We did this, initiating the figure there. Initiating triangles. Yeah. Cool. What is this? What is this symbol? What is even this symbol? I don't know. A T. Well, I don't think so. Length of a subset. zero probability. Indeed, if the unit interval had a countable number of elements, with each element having zero probability, then the additivity axiom would imply that the whole interval has zero probability. Right. Contradict the normalization axiom. Bend any rounds less than figure 1.6. What is this, like the opposite of belongs? No. I don't know. I don't remember. The probability of the union of A and B, what is less or equal to the probability of A plus B. Yeah, sure, definitely. Yeah, this is like here. AI. Share this report probability to the sets AA. 1, 2. Suitably defined sample space. I don't know how rules the guy this instead. Hmm. Tractability. Transferability of the trackability of person skills and professional experience. Skills and chapter saying. Yeah, this is interesting. I kind of agree with this. Intersection. The complement of A intersection B, which all this is the complement of A. No, all this is the complement of A. Intersection B should be this whole thing. Oh yeah, only this. Yeah. Cool. Okay. Yeah, that's what I did. Brilliant. Verifying property B. We may probably need. What the fuck I need this? density. What the fuck? So interesting, man.
Bijective mapping.
Un solo oído, hermano. Zero theorem term? No, zero probability term. Muy. Problem density and measure zero. Measure zero. Right.
Bijective mapping. A map is called bijective if it is both injective and surjective.
Surjective? What the fuck? Oh, one to one, onto. What do you mean?
Injective is one-to-one mapping.
Like functions?
Surjective is onto mapping. Bijective
Oh, that's
mapping.
crazy, man.
A
Excellent
map is
explanation.
called
What? We're just
throwing a
problems.
die.
We want to do it. Hmm. The output. No. Oh yeah. There's the input. That's the output. This is not probability. It is a probability density. Like that. The heaviest part of the bell curve. The heaviest, or the, you know, the most, the one with the most density. Dense, the most dense. And they're in the curve between 2 points using calculus. Yeah. Right, cool. Here at that point. How many steps, no deviations you are away from the absolute average, which is absolute average. Oh, that's what it is called. That's what it is called. Euler's number. Well, why? All this cannot be E, or is it initial decay? All this things are dropping off quickly. The exponent. Wow. Wow, brother. That's interesting. This is the engine of the bell shape. The engine. Square bar x squared force the curve to be perfect. It's perfectly symmetrical. Yeah, sure, of course. And over 2 just means that it is expanded. Oh no, what the fuck? The square makes them both 4. That means the left side of the bell is a perfect mirror image of the right side. Say that again. Yeah, sure. The negative sign means that as x gets further from 0, further from the average, the height of the curve rapidly crosses towards 0. This is why extreme outliers like a 7 foot tall human are incredibly rare. Huh. I done. They call the rule. I don't know what you mean. What's equal? Oh yeah, sure. Mathematician multiply the whole formula by 1 over square root of 2 pi. But why 2 pi though? Standard, bro. Total number of heads. Not yet, bro. Not yet. Economics, retrans, bro. This is this fucking guy. Oh, with 3 blue, 1 brown. I just want to see a short video. Yeah, just a fucking short. For now.
We know that the odds of us existing were extremely low. Like, for you to actually be alive right now, on this planet, in this
bro, what?
galaxy, in this universe, billions, if not trillions, of odds had to be defied. And somehow, against all of them, you're sitting here watching this video. Or are you? Ludwig Boltzmann, a physicist who was nominated.
No. That's a completely different thing, bro. Barber paradox. Really?
And you have continuous random variables.
Box paradox. Now it's a box. It's impressive.
Continuous. And discrete random variables, these are essentially random variables that can take on distinct or separate values. And we'll
whatever. Let me see. Yeah, let me see
give examples of that in a second. So that comes straight from the meaning of the word discrete in the English language. Distinct. Distinct.
Here's a circle with an equilateral triangle inside. Question.
Chill, bro.
What's the chance a random chord is longer than the side of the triangle?
I don't know. 0?
It actually depends on which method we use to generate our random chords. Let's take a look into the first method of picking random, the random endpoints method. Pick one point on the circle, then choose the other endpoint uniformly across the circumference. Only 1/3 of those chords are longer than the side of our... our equilateral triangle, giving us a probability of 1/3. A second way to view this problem is the random radial distance method. Pick a random point along a radius of the circle, and then draw the chord perpendicular to that radius. Any point past the midpoint of the radius, close to the center, will produce a chord longer than the side of the equilateral triangle. This gives us a probability of 1/2, which differs from our 1/3 probability from earlier. The final method is the random midpoint method. Pick a random point inside the circle to serve as the chord's midpoint. If it falls inside the smaller central circle with half the radius, the resulting chord will be longer. The area of the inner circle is 1/4 of the whole circle, giving us a probability of 1/4. Same question, 3 methods of randomness, 3 answers. That's the Bertrand paradox. The odds depend on how you choose to be random. Here's a circle with an equilateral triangle inside. Question, what's the chance a random chord is longer than the side of the triangle? It actually depends on which method we use to generate our random chords. Let's take a look into the first method of picking random, the random endpoints method. Pick one point on the circle, then choose the other endpoint uniformly across the circumference. Only 1/3 of those chords are longer than the side of our equilateral triangle, giving us a probability of 1/3. A second way to view this problem is the random radial distance method. Pick a random point along a radius of the circle, and then draw the chord perpendicular to that radius. Any point past the midpoint of the radius, close to the center, will produce a chord longer than the side of the equilateral triangle. This gives us a probability of 1/2, which differs from our 1/3 probability from earlier. The final method is the random midpoint method. Pick a random point inside the circle to serve as the chord's midpoint. If it falls inside the smaller central circle with half the radius, the resulting chord will be longer. The area of the inner circle is 1/4 of the whole circle, giving us a probability of 1/4. Same question, 3 methods of randomness, 3 answers. That's the Bertrand paradox. The odds depend on how you choose to be random. Here's a circle with an equilateral triangle inside.
Distinct or separate values, while continuous, and I guess there is just another definition for the word discrete in the English language, would be polite.
What do you mean? How continuous is going to be a different, another
While
definition?
continuous, and I guess there is just another definition for the word discrete in the English language, would be polite or not obnoxious or kind of subtle.
fuck?
That is not what we're talking about. We are not talking about random variables that are polite. We're talking about ones that are ones that can take on distinct values. And continuous random variables, they can take on any value in a range, and that range could even be infinite. So any value
It can be
in an interval, in
infinite interval.
an interval. So with those two definitions out of the way, let's look at some actual random variable definitions. And I want to think together about whether you would classify them as discrete or continuous random variables. So let's say that I have a random variable capital X, and it is equal to, well, this is one that we covered in the last video. It's 1 if my fair coin is heads. It's a 0 if my fair coin is tails. So is this a discrete or a continuous random variable? Well, this random variable right over here can take on distinct values. It can take on either a 1 or it could take on a 0. Another way to think about it is you can count the number of different values it can take on. This is the first value it can take on. This is the second value that it can take on. So this is clearly a discrete. This is a discrete random variable. Discrete random variable. Let's think about another one. Let's define random variable y as equal to the mass of a random animal selected at the the New Orleans Zoo. New Orleans Zoo, where I grew up. The Audubon Zoo. At the New Orleans Zoo, the Audubon Zoo. Y is the mass of a random animal selected at the New Orleans Zoo. Is this a discrete random
I mean, we don't know,
variable
bro.
or a continuous random variable?
We don't fucking know. What if he weighs exactly fucking 20 kilograms, you know?
Well, the exact mass, and I should probably put that qualifier here. I'll even add it here just to make it really really clear. The exact mass of a random animal or a random object in our universe, it can take on any of a whole set of values. I mean, who knows exactly the exact number of electrons that are a part of that object right at that moment? Who knows the neutrons, the protons, the exact number of molecules in that object or part of that animal exactly that moment? So that mass, for example, at the zoo, it might take on a value anywhere between, well, maybe close to zero. Close to zero. There's no animal that has zero mass, but it could be close to zero if we're thinking about an ant, or we're thinking about a dust mite, or maybe even maybe if you consider even a bacterium an animal. I believe bacterium is the singular of bacteria. And it could go all the way. Maybe the most massive animal in the zoo is the elephant of some kind. And I don't know what it would be in kilograms, but it would be fairly large. So maybe you can get up all the way to 3,000 kilograms, or probably larger. Say 5,000 kilograms. I don't know what the mass of a very heavy elephant, or a very massive elephant, I should say, actually is. Maybe something fun for you to look at. But any animal could have a mass anywhere in between here. It does not take on discrete values. You could have a animal that is exactly maybe 123.75921 kilograms. And even there, that's actually might not be the exact mass. You might have to get even more precise, 10732. And I think you get the picture. Even though this is the way I've defined it now, a finite interval, you can take on any value in between here. There are not discrete values. So this one is clearly, clearly a continuous random variable. Continuous random variable. Let's think about another one. Let's say that random variable y, instead of it being this, let's say it's the year that a random student in the class was born. Random student in a class was born. Is this a discrete or a continuous random variable?
No, that's a year. That's a year. Fuck yeah, it's fucking discrete.
Well, that year, you literally can define it as a specific discrete year. It could be, it could be 1992, or it could be 1985, or it could be 2000 and 2001. There are discrete values that this random variable can actually take on. It won't be able to take on any value between, say, 2000 and 2001. It'll either be 2000, or it'll be 2001, or 2002. Once again, you can count the values it can take on. Most of the times that you're dealing with, as in the case right here, a discrete random variable, and let me make it clear, this one over here is also a discrete random variable. Most of the time that you're dealing with a discrete random variable, you're probably going to be dealing with a finite number of values, but it does not have to be a finite number of values. You can actually have an infinite potential number of values that it can take on, as long as the values are countable, as long as you can literally say, okay, this is the first value you could take on, the second, the third, and you might be counting forever, but as long as you can literally list, and it could be even an infinite list, but if you could list the values that it could take on, then you're dealing with a discrete random variable. Notice, in this scenario with the zoo, you could not list all of the possible masses. You could not even count them. You could, you might attempt to, and it's a fun exercise to try at least once to try to list all of the values this might take on. You might say, okay, maybe you could take on 0.01 and maybe 0.02, but wait, you just skipped an infinite number of values that it could take on, because it could have taken on 0.011, 0.012, and even between those, there's an infinite number of values it could take on. There's no way for you to count the number of values that a continuous random variable can take on. There's no way for you to list them. With a discrete random variable, you can count the values. You can list the values. Let's do another example. Let's let random variable z, capital Z, be the number of ants born tomorrow. Born tomorrow in the universe. in the universe. Now, you're probably arguing that there aren't ants on other planets, or maybe they're ant-like creatures, but they're not going to be ants as we define them. But how do we know? So,
Yeah, that shit definitely.
number of ants born in the universe. Maybe some ant tomorrow. We can count the number of values this could take on. This could be 1, it could be 2, it could be 3, it could values variable. Well, let's say a random variable x. So we're not using this definition anymore. Now I'm going to define random variable x to be the winning time. Now let me write it this way: the exact winning time. Exact winning time. Winning time for the men's 100 meter dash. The exact time be actually dash of the 2016 Olympics, and not the one that you necessarily see on the clock. The precise time that you would see at the men's 100 meter dash. Is this a discrete or continuous random variable? It could be 9.5 the Olympics. Same time, exact number of seconds it takes for that person to, from the starting gun, to cross the finish line. And there, it can take on any value. It can take on any value between, well, I guess they're limited by the speed of light, but it could take on any value you could imagine, and it might be anywhere between 5 seconds, and maybe 12 seconds. And it could be anywhere in between there. It might not be 9.57. That might be what the clock says, but in reality, the exact winning time could be 9.571, or it could be 9.57235.9. I think you see what I'm saying. The exact precise time could be any value in an interval. So this right over here is a continuous random variable. Now, what would be the case, instead of saying the exact winning time, if instead I defined x to be the winning time of the men's 100 meter dash at the 2016 Olympics, rounded to the nearest hundredth. Is this a discrete or a continuous random variable? So let me delete this. I've changed the random variable now. Is this going to be a discrete or continuous random variable? Well, now we can actually count the actual values that this random variable can take on. Variable now. Is this going to be a discrete or continuous random variable? Well, now we can actually count the actual values that this random variable can take on. It might be 9.56, it could be 9.57, it could be 9.58. We can actually list them. So in this case, when we rounded to the nearest hundredths, we can actually list the values. We are now dealing with a discrete random variable. Discrete random variable. Anyway, I'll let you go there. Hopefully this gives you a sense of the distinction between discrete and continuous random variable.
That you put that in the end of the video is kind of crazy, but that's really good. Really
So
good.
I want to tell you about.
Shut up, bit. Because my bad drawing doesn't function. My bad drawing. Otra vez están cachando el gato, weón, puta madre. Oh yeah, that's exactly what I just saw. Just saw chord through midpoint, chorded angle. randomly chosen. How? What is it, theta? I don't know. That shit ain't theta, bro. Your line was made equally likely. We consider the coordinate with intersection of the circle. For elementary geometry, the length chord is greater than the side of the triangle if omega. It's not omega either. It's between pi over 3 and 2 pi over 3. Since the fuck? Since theta, let's say theta, okay? Takes magnitude 0 pi. Huh? The mean of the center, yeah. Mu. Is that what you call it? The mean, okay. Not the average, but the mean. Which means the most fuck you. The most happened event, the most data point happened. I don't know how to say it, bro. The highest frequency. Yeah, what is standard deviation? This? How the fuck this is standard deviation? Color curve. I don't get it. What the fuck? 90, 60, 90, qué chucha, man. I'm sorry. Oh my god. Which is true. Hmm. Omega? That's what I am. Sigma. Yeah. Just good. It's fucking good. So usually we only have 3 standard deviations, so what is the limit? Come on. No liars. Yep. Okay. Really? I think I kind of understand this, but I would like to watch a video, and I think this one is the right video.
A classic paradox in probability that is sort of a cautionary tale.
Oh, this thing is fucking 3 blue, 1 brown?
For students when they're about to hear a puzzle or they're setting up.
Wait, hold on. Who's number 5? Isn't that the same guy? My love pie. 4 days ago. Oh, this. She. Is that her? Is she really her? I don't think so. Who's number 5, bro? Who's here? Who's she? Attempts are hard. I love her. I really love her, man. She's so cute. Okay, who the fuck is number 5? For real. Or is it just a guy with many guests? I don't think so. Who the fuck is number 5? Yo. Beatties with numbers and mathematics. Brandy Harlan since Jane Street. Who's Jane Street? I think it's the girl, right? No, Jane Street is a quantitative transfer. Jane Street, what the fuck? Calculus, and there's the fucking Indian flag. What the fuck? 99 kilo Sudoku. What are you even talking about, man? Who's she? I love her. I fucking love her. Hannah Fry. Yeah.
Hey there everyone, we have a number file video.
Yeah, fucking love her.
Some kind of problem. Bertrand's paradox. There was a person who wrote this probability textbook, last name Bertrand. He mentioned in there why you have to be very careful with probabilities when infinity is involved. So what I'm going to do is have a circle, and I'm going to draw a random.
You know what I'm gonna do? Wow, 2 million followers. Cambridge University, oh my god. Nah, me voy a cambiar de universidad solo para conocerla. Nah, me quiero casar con ella a pesar de que tiene 42 años. Yikes. Nah. No, tiene husband. I don't know ya. It's you that one. Wait, what is wet? Widow, right? To take a suppose. No, pensé que era viuda. Grade A gold star. Wow. She made an hinge. Like. Bueno. Wait, what? Wait. Who is Phil Little? Oh, it's a writer. What the fuck? Well, I don't know. Bueno, pues qué chuchazo, weón.
Chord somewhere in that circle. So a chord is something that just connects two different points on that circle, right? What I want to ask is a certain question about the distribution of the length of this chord. You know, there's some kinds where if it just glances through the circle, that length will be very short. If it went through the diameter, that length would be very long. One of the most natural questions you might ask is something about the mean of that length. But that turns out to be a little on the messier side for the cleanliness of what Bertrand wanted to do. So instead he says, compare that length to the length of the sides of an equilateral triangle that's inscribed
This nigga's Russian, right?
in that circle. Which might seem kind of weird, like why are we talking about triangles? But it turns out to make the answer especially clean. So if we take some equilateral triangle, where, forgive the fact that I'm a little curved in the side length there, and we call this side length something like S. What Bertrand asks is, what is the probability that the length of your random chord is bigger than the side lengths of that triangle? And we could get a little numerical about this. If we say that the circle has a radius of 1, then geometry students might remember their 30, 60, 90 triangles. This angle here is 30 degrees. This angle here is 60 degrees. And so this side length will be exactly 1/2. This side length will be square root of 3/2. So we could also say, if it's a unit circle, what we're asking about is the probability that the length of our chord is bigger than the square root of 3. So just a simple question, like anything else you might come across in some books, some list of exercises at the end. And let me show you how to solve it. It's really not that hard. Without loss of generality, you can assume that the first point is one of the corners of the triangle. If it wasn't, we could kind of rotate the triangle so that was the case. And then we weren't given any specifying information about the nature of the chord. So we'll assume that the next side is uniform somewhere around this circle. If the second point chosen was over there, we would have a chord that's shorter than the side lengths of the triangle. If it fell into this kind of critical region on the opposite side of the triangle, up here, that region, then the chord that you draw would be longer. And then similarly, if it was on this other side, it would be shorter. So, probability student, they're doing their homework. They say, what's the probability this is longer? Not a problem. It is going to be exactly 1 in 3. because the circle's evenly divided into 3 pieces. Oh, there's only one of those pieces that will give you longer chords. Said and done, not an issue.
So if any random chord, there's a 1/3 chance it's going to have that long.
Yeah.
Yeah.
No paradox to be found. In fact, let's verify this empirically. I ran a simulation. Essentially what I do is I choose a random pair of points somewhere on the circle, I connect them, and then I'm going to count whether or not that ends up longer than what we need, and then basically ask the proportion where that's the case. And I'll color it blue whenever it's longer, and then white whenever it's shorter. I'm just going to have this simulate a whole bunch. It'll do on the order of 1,000. And this ratio will be telling us what proportion of them are longer than the length we care about. And yeah, it seems like it's going roughly on the order of 1/3, so 0.33, kind of oscillating 0.44. So we did it theoretically, we did it empirically, we have an answer. So another...
Cool. Okay. I'm gonna finish this tomorrow. See you.